Hi, and welcome back to Basic Logic, an open introduction. In this video series, we're working through many of the chapters of For All X, the Lorain County remix, an open source logic textbook you can download right now. Just Google it and follow along. The last few videos, we've been looking at Chapter 8, a derivation system for sentential logic. In the last video, I talked about the introduction and elimination rules that allow you to directly manipulate the syntax of sentences of SL to prove that arguments are valid and show that some sentences follow as entailments. They're entailed by certain other premises. These rules are actually complete. They allow you to do anything you need to do. You can prove that things are tautologies, even though we haven't quite done that yet. You can show that arguments are valid. But let's make life a little easier on ourselves. Earlier I talked about substitution instances. That's the idea that if you have two logically equivalent sentences, you could just swap them out for each other. So let's add some substitution instances into our inventory of actions in the game of derivations. And let's see how much more powerful the derivation system can become. So here's our first rule of replacement. It's called De Morgan's law. It allows for the substitution of logical equivalencies between disjunctions and conjunctions, between or and. Here they are. First one is not the case that both P and Q is equivalent to either not P or not Q. The second one says, writes the negated disjunction in this case, neither P nor Q is equivalent to not P and not Q. Boy, that rule would have really been useful in our last derivation. Too bad we didn't have it, but we don't need it. This is just going to make our lives easier. So, in addition to all the introduction and elimination rules that we already have, we can add to our list De Morgan's law, and we can appeal to it in the process of our derivation. Importantly, we can demonstrate this equivalency using the basic introduction and elimination rules that we already have. So if I wanted to prove that neither P nor Q entails not P and not Q, I can do that. It'd be a long and fairly tedious derivation to do using only the intro and elimination rules, but you could do it. So natural deduction systems, and every textbook has its own, typically come with a set of additional substitution and also replacement rules that are kind of similar to De Morgan's. Another one is called implication. This relates the conditional to the disjunction. So for any conditional, you can turn it to an equivalent disjunction and vice versa. So if you have an if P then Q and you'd rather have a disjunction for whatever reason, you could turn it into a disjunction. And if you have a disjunction, you can turn it into a conditional. Now, the replacement and substitution rules kind of chosen to be part of any natural deduction system. They're chosen because they're useful. But any substitution and logical equivalence can be used. And it won't harm the validity of the derivation or the entailment. It won't hurt the system. De Morgan's and implication are typically the two most important ones that you're going to use and appeal to most often. Another one called transposition comes in kind of a distant third, which is for any if P then Q, you can substitute it with if not Q, then not P. So here's a screenshot from one such logic textbook. Here are all the rules of replacement. You see there's implication over here, double negation, De Morgan, transposition. Some other complex ones like exportation don't get used that often. What's important to remember for all the rules of replacement and kind of substitution kind of rules is that P and Q here, again, they're meta variables. When I say you can turn a conditional into a disjunction, it's really any sentence of SL where the main logical operator is a conditional. You can turn that into a disjunction no matter how complex either side is. As long as the main logical operator has that, is a conditional, has that form that we're looking for. This is really going to help make derivations faster and easier because you can appeal to them. For example, in the derivation in the last video, I needed to turn a negated disjunction into a contradiction so I can actually release it. But if I had the De Morgan's rule that allowed me to turn the negated disjunction to a conjunction, it would have been a lot faster. In fact, if you want to go back to the previous video and try to do it using De Morgan, you'll probably finish it in like 3 lines. Now, one rule I always really wanted, which hasn't been available in most natural deduction systems, has to do with negated conditionals, right? So if I say not the case that if P then Q, that's actually logically equivalent to P and not Q for obvious reasons having to do with the truth table. Because the only case where The conditional is false is when the antecedent is true, but the consequent false. So it's typically unnamed. I think it's just called negated conditional when I Googled it. But the equivalency is easy to show with the truth table. One of the interesting things, however, is that for some basic cases, the natural derivation system is actually more complex than the truth table. The derivation to show this using only the intro and elimination rules is something like 20 lines long. I'm not going to do it right now. It's actually super boring. But if you pause the video, you can try to figure it out yourself. It's actually one of the really kind of an interesting logic puzzle to do it using just the intro elimination rules. But you can appeal to negated conditionals in your derivations. Now, I'm kind of going very fast and just saying, look, these rules exist. But you should just write them down, make kind of a cheat sheet, and appeal and remember them. Remember that you can turn a disjunction into a conditional under certain circumstances. That a negated disjunction can also be turned into a conjunction under certain circumstances. There's some other rules that are not quite substitution or replacement rules and not quite intro-elimination rules. And we're going to add these to our inventory, our grimoire of logic spells. One of them is known as modus tollens, which is Latin for the mode of denying. Right? Everything in Latin sounds cool and occult, right? And it goes a little bit like this. If P, then Q, not Q, therefore not P. Think about the truth table for a sec. This makes a lot of sense. If we have, for any conditional where the antecedent is false, where the consequent is false, the antecedent has to be false too. Otherwise, the conditional itself wouldn't be true. How do I prove it using the ordinary elimination rules? Very easily. If P, then Q, not Q. Those are my premises. If I assume P, I can get Q, but I also have not Q, the reiteration here, so there's a contradiction. So not P has to be true. We can also sit down and look at the truth table for it. The truth table for if P, then Q, again, if the antecedent is false, if the consequent is false, the antecedent also has to be false. So modus tollens, if you see anything of the logical form if P, then Q, and you have not Q, you can derive not P. We're going to be using all of these in some of the exercises that are coming up. Another rule is hypothetical syllogism. This is also fairly easy to prove using intro and elimination rules, but for any case where you have if P, then Q, and if Q, then R, you could just go ahead and claim if P, then R. Finally, we have disjunctive syllogism, which is, well, okay, that's basically the elimination rule for the disjunction, but this is from a different text, so we already have that one, so we're just going to forget it for now. So modus tollens, hypothetical syllogism are the ones we're interested in. All right, so here is what they are, the important ones, the top 8 rules of replacement. Refer back to this slide while you're doing exercises. All right, we have implication, De Morgan, transposition, double negation, commutation, which just allows you to flip things over. Often, when I'm grading these things or when I'm teaching, I say just ignore commutation, just do it, just go directly to the order you want. And negated conditional, which I say is a useful rule everyone should use. So, I've already talked about modus tollens and hypothetical syllogism. This is a huge information dump, right? You should just kind of be taking notes and looking at these kind of logical forms, these substitutions, and these inference rules. Constructive dilemma is a pretty interesting one as well. So here's a rule that says, suppose you have a disjunction. And from that disjunction, the same consequence follows from either side. Therefore, that consequence follows. So if I say, look, either P or Q, right? If P, then R. If Q, then R. So R is going to be true, right? Look, either I'm rich or I'm not. If I'm rich, I'll be happy. If I'm not rich, I'm going to be happy. So I'm just going to be happy, right? That argument is valid, so that's a useful inference rule you can appeal to. All right. So now we have a whole bunch of new tools. And with these powerful new tools, it'll be easier to do some more powerful new things. One of the things I haven't really talked about yet, although I hinted at it, is that you can not only use the derivation system to verify whether an argument is valid, which is very easy. All you need to do is derive the conclusion from the premises. You can also verify if something is a tautology. How does that work? If you want to prove a tautology, just remember that a tautology is something that's always true. It doesn't matter what's happening out in the world, as it were. no matter the values of its components, it's always going to come out true under the main logical operator. We can represent this by basically starting a derivation without any premises. If you have a derivation without premises and you prove something, you can therefore show that that statement must be a tautology because it doesn't depend on anything. Right? It doesn't hinge on anything being true in advance. So, for example, how am I going to do this? How can I do a derivation without any premises, without nothing to work with? Well, you can always use the introduction rules that require hypotheticals, because then you can introduce whatever the heck you like. And if you can discharge something on the main scope line, on the main line on the left, then that will definitely be a tautology because it didn't depend on the assumption of anything prior. Here's the simplest case. Suppose I start with no assumptions whatsoever. I assume P. Well, if P is true, you know what else is true? P. So I can discharge if P then P, which is a tautology. Right? We all know the truth table of if P then P. Right? It's true, 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 false, false, true. So if P then P is a tautology. Now, if you're able to generate a sentence without premises, that's a tautology. But notice if I had premises, I could still generate the tautology. I could still make all those moves. It's just that if I just start with no assumptions, I make it really, really clear that I'm working without assumptions, and therefore it's a tautology. All right. Here's another example. Suppose I want the tautology either P or not the case that P. This is a nice example because it's going to start leveraging some of these extra rules that we have, like De Morgan's. So I have no premises, and I want either P or not P. What am I going to do here? Well, I need to construct a disjunction. Constructing a disjunction is hard because disjunction introduction requires a one or the other side I already have, but I'm not going to get either of those things. So what I should do is just deny the tautology. So I'm going to go, it is not the case that either P or not P, which of course, whoop, we lost power. Where's the lights? Lights. They're back. So if I deny it, I get a negated disjunction. Using De Morgan's law, I know negated disjunctions are equivalent to conditional statements, conjunction and statements, where either side of the and has a not in front of it. Because like neither P nor Q is just as equivalent to not P and not Q. Here, things get a little fuzzy around the edges because it's not the case that P and or not P. So I've got to make sure that I'm applying the rule right, that I'm going, right, neither P nor Q is equivalent to not P and not Q, so not P here and not Q, in which case the Q is not P, so it's not P. So P and not P. That's an and statement. I can deconstruct the and statement into its two components, so I get P and not the case that not P, which is a contradiction. Or I can double negation it and show P and not P directly. Either way is fine with me. I'm not, most probably your professors won't mind. If they have a preference, they'll let it be known. And here we have our contradiction, and then we can discharge the opposite, therefore P or not P. We discharge the opposite, showing that it came from no premises, therefore either P or not P is a tautology. All right. Again, my strategy was to assume the opposite and derive a contradiction. Where's my next slide? Oh gosh, there's no next slide. Okay, let's do a bunch of examples then. So I ran out of slides. Let's do some examples. I did a bunch of, it's like an info dump of all the rules of replacement and substitution instances and that sort of thing, the inference rules. So hopefully you have them under your belt, you wrote them down. You're following along with the chapters in For All X, which I'm following around kind of loosely. But here's another example of a derivation. We have if D then E, if E then Z of W, either not Z or not W. And what we want to prove is not the case that D. So what we're hoping to show is a negated atomic sentence. We have a bunch of conditionals and a disjunction. What should be our strategy here? Well, we could assume the opposite and go for the conclusion. That seems promising because if I assume the opposite of not D, that's just D. And that gives us a chain of kind of like logical consequence because of the conditionals. So why don't we start with that and see what that gets us. Sometimes it's better to just have an idea and try it out. No idea if this is going to work. I haven't done this exercise in a long time. So let's assume the opposite, D. Why am I doing it? Because it is a disjunction, not disjunction, negation, introduction. So it's my assumption or my sub-assumption. So there it is. So now I have D as a hypothesis. Anything I derive from D could be discharged as a conditional. That's not what I'm doing, of course. What I'm actually doing is looking for a contradiction, so I can discharge the opposite, not D, right? Because your hypothetical line, you have to be kind of committed to a course of action. So from D, we can, of course, get E. From 4, 1, conditional elimination. Then over on 6, we have both Z and W. Z and W, of course, comes from 5 and 2, another conditional elimination. So far, so good. Now we have an interesting dilemma. We're looking for a contradiction, and we know there is one somewhere. So we know that these two things can't be true simultaneously. Either not Z or not W. One of these has to be, they're saying like either not Z or not W, but I don't know which one. But this line over here says both Z and W, definitely. So how do we make that contradiction really explicit so we can finish this derivation and discharge not D, which is our target sentence? All right, so think about it for a few seconds. That's where we're stuck. How are we going to do it? All right, so you might be thinking, well, okay, it's a conjunction. Maybe I could get Z and then use disjunction introduction or not W. That's not exactly going to work. However, what we do have is rules of replacement. If you remember what they are, you remember that De Morgan's law allows you to switch between conjunctions and disjunctions, provided they have the right form. So let's look at one of those rules right now. So we know that neither P nor Q is equivalent to not P and not Q. That doesn't help us. However, we have another rule that says either not P or not Q is actually going to be equivalent to not both P and Q. This one's going to be useful. Why? Because we have something of this form here, right up on sentence 3, either not Z or not W. So I can appeal on line 7 to De Morgan's law, which is one of our extended rules, and say, actually, you know what? Not the case that both Z and W. Now I've made the contradiction explicit. This is from 3 De Morgan's law. So now De Morgan's law has made really explicit this contradiction. De Morgan's law is useful because otherwise I'd have to do a whole bunch of nested conditional hypothetical proofs in order to bring to light the fact that these statements are contradictory. But De Morgan's law allows us to skip that stuff because we know that this is logically equivalent to that. Therefore, down here, I can simply derive not the case that D. Okay, I'm going to pause the video, erase the board, and come back with another example. So here's another example of a fairly complicated derivation that will require use of the rules of replacement. Well, they won't require it because you can always do it using the intro and elimination rules, but we'll require them to do it efficiently in a way that's not a giant pain in the butt. So here we have two fairly complex premises. At least premise 1 is complex. What we have is a AND as the main logical operator. Inside that AND are some conditionals, so probably we're going to want to break that down. Here also we have an AND. That's very useful. We're going to want to break that down into its component parts, no doubt. But let's look at that target sentence that we're trying to derive. We have not B and F. So we have 3 ANDs. The AND, to construct it, we're going to need both of them to be true. So we're going to need that not B, and we're going to need the F. How are we going to get it? Well, let's see. Where's that F? That F is over here. It's the consequent of this conditional here. So if we had C, we can get F. Do we have C? It's over here. Great. Why don't we start there, and then we'll puzzle out the rest as we go. This is low-hanging fruit. So we have C. Where do we get it? From 2. And that is, of course, a AND elimination, conjunction elimination. 4. If C, then F. Remember, we can't skip steps. We have to be explicit about all our steps. If C, then F. That's really useful. Well, how do we get it? We got it from 1, also a conjunction elimination. Step 5. We can finally get F over here, so we have 1/2 of our target sentence in 3 moves. How did we get it? We got it, of course, from 3, 4 conditional elimination. Awesome. So What's our next step here? We need to get B somehow. Well, or sorry, not B. How are we going to get not B? Here's where things get a little bit more complicated. We know that B is over here on the other side of the conjunction, so maybe we should just get it out of there, get that conjunction out, and see what we can do. G and C. How did we get that? From one conjunction elimination. Good. What's next? Well, we have to get that not B somehow. How do we get it? Well, when we look at a not B, one way to do it would be obviously to assume the opposite and get a contradiction. So for example, I could assume B, that would be the antecedent here, then I get G and C. Then maybe I'd be able to get a contradiction with not G. That's one way of doing it. It would introduce a conditional proof. But actually, while that way would work and be fairly quick, there's an easier way. Here's how it would go. We'll require these extended rules of inference and substitution. The rule I'm going to go after is something like this. If P, then Q, not Q, therefore not P. Modus tollens, the way of negation. So what I would need here to get the not B is the not the case at both G and C. How am I going to get that? Well, I have not G already. Well, not already, it's just very easy to grab from 2, another conjunction elimination. Then I can use, I know I love this, it feels like a magic trick every time. I can just introduce any disjunction I like for any reason at any time. So either not G or not C. Now if you remember De Morgan's law, what we have down here, is this actually less complicated than the conditional, than the negation? I don't know, doesn't matter. I get not the case that both G and C. So let's justify some of these rules here. This is 7, disjunction introduction. This is 8, De Morgan's. I grabbed it from 8. I transformed it using De Morgan's law. Now I have if P then Q, right? This is my P, this is my Q, this is my not Q. So by rule, over by number 10 here, I get not B by application of modus tollens, which is one of the rules we just talked about very briefly as I kind of ran through these extra rules you can do. But telling you about them is not as useful as actually using them, so let's use them. How did I get there? Well, I got it from 6 and 9. I'm going to go MT for the modus tollens rule. So now I have not B, I have F. So I'm just going to dot, dot, dot. We're going to keep going. This is line 11. I have not B and F. How did I get it? I got it, of course, from lines 10 and 5, conjunction introduction. And that's our proof. Now, if you want, you can sit down and write out the way of doing it by assuming the opposite, right? Assuming B and then deriving a contradiction. That would work too. It might actually be a good exercise. I'll be right back with a new exercise. All right, here's another exercise. This time we're going to try to prove a tautology using our derivation system. How do we do that? Well, a tautology is a derivation, roughly, without any premises. So let's try that out. Here's our tautology. I'm telling you it is. No trick questions. Okay, so it's if not P or Q, then if P, then P. All right, so let's try that out. So 1 over here, no premises, 0 premises. Let's start. Now, whenever you have a tautology, you know you're going to need to start by making some kind of assumption. And then you're going to have to discharge that assumption. That's the really important part. So what we need to do is determine whether we're going to use conditional introduction or negation elimination, something like that. One way to do it would certainly be to, because we know it's a tautology, negate the whole big sentence and derive a contradiction. We'd have a negated conditional, so if we wanted to use our expanded rule set, negated conditional would give us actually a lot to work with, because we would have not, if we negated this whole thing, we'd have this true and that false. And if this was false, if P then P is false, we could probably get a contradiction pretty quick. That'd be one way of doing it. Another way would be to use conditional introduction. Why don't we try that strategy? So, if I'm going to go for conditional introduction, the first thing I'm going to want to do is just introduce my antecedent. So anything that follows from this antecedent I can discharge as a conditional. If this, then anything I derive. So this is my sub-assumption for conditional introduction. Good. Now I need to build if P then P. So I want to build, as a consequent, another conditional. And if P then P is actually a pretty trivial tautology to build. So why don't we just build it? I assume P as a sub-assumption, and then I reiterate P. So this is my sub-assumption for another conditional introduction, and now I'm just reiterating it. If I assume P, you know what else is true? Well, P. So if P, then P. This is a pretty simple tautology to prove. I assume this antecedent because I can, and because my consequent is a tautology, that would also be easy to derive. So then I just discharge the whole thing on the main line. So if not P or Q, then if P, then P. And why is this a tautology? This is the worst arrow ever. Well, if the consequent here is always true, then this thing can never be false, because the only case where this is false is where you have true false, but this is always true. So any conditional where the consequent is a tautology will have to itself be a tautology. Should we do it the other way? So this was the easy way where we assumed the antecedent and derived the consequent. Let's do it a slightly harder way. Well, I'm not sure it'll actually be harder, I just haven't done it yet. So let's assume the whole thing is false. Not the case that, I have to make another bracket, not P or Q, therefore P, then P, close, close. So that's lots of brackets, negated this. Now I say we can use the negated condition rule, but the fact is a lot of textbooks say that rule doesn't actually exist. In my classes I always say, sure, use negated conditional. It's absolutely a valid inference rule. So it's actually kind of a substitution instance rule. So why don't we do that? Just to, otherwise we'd have to, we'd have to assume more nested sub things. So let's just do it the easy way. So we have a negated conditional. There's only one way a negated conditional could be true. It's when the antecedent is true but the consequent false. So we're going to get, change this to not P or Q, bracket, bracket, and not the case that if P, if P, then P. So let's break that down again. What I have here is not the case that if P, then P, so I'm denying that P follows from itself. And of course, why don't I just run negated conditional again, because I love that rule so much. What we have is P and not P, which gives us P, not P, contradiction. I can discharge the sentence here, which I'm not going to write out because I'm lazy. You know what, let's just write it out. Okay, and 8, not P or Q, then if P, then P. That's how you do it with negated conditional. Now suppose you didn't have negated conditional in your bag of tricks. How would you do it? I'll leave that as a question to you, the viewer. I'll be right back with a new question. All right, here's another exercise where we're going to try to put some of these different skills together. So far we've been looking at sentences of SL directly. But way back a few chapters ago, we were actually translating things from English to SL and then verifying validity. Now, of course, verifying validity is only as good as the translation you have. But let's just see if this argument is logically valid. We're going to use some following letters here, but let's just kind of read the passage and see if we can find the conclusion. If I work hard at my job, then I'm going to get promoted. And if I get promoted, my parents will be happy, unless they think my job is useless. Well, either I won't be on time, or I'm going to work hard at my job. And of course, my parents don't think my job is useless, so I can safely conclude that if I'm on time, my parents will be happy. This is actually an old exam question of mine. I put lots of conclusion indicators because really I don't want to try to trick people. I just want to make sure that they get the translation of the derivation right. So let's start by translating these sentences. I'm going to do them up on the board here, then I'm going to full screen the video afterwards. If I work hard at my job, then I'll get promoted. That's a pretty easy, I think, sentence to translate. If I work hard on my job, then I'll get promoted. That's W for work and P for promoted. If W, then P. Good. Now we have another premise. And if I get promoted, my parents will be happy, unless they think my job is useless. So what we have is two parts, right? If I get promoted, they'll be happy. So we know there'll be like an if P then H, something like that. But there's an unless. unless they think my job is useless. If you remember unlesses, you know that they're also conditionals. They're conditionals that'll have like a little negation. They're saying it will happen unless something prevents it. So one way to do that would be to say, if it's not the case that they think my job is useless, then if I'm promoted, they'll be happy. That kind of captures the sense of the unless. If not useless, then if promoted, then happy. So they will do that unless. So if not useless, then if promoted, then happy. Next premise. Either I won't be on time or I will work hard on my job. So let's go for like not, why did I say Y instead of T? That's bizarre. All right, doesn't matter. Either not Y or I'll work hard on my job. Lots of premises to work from, lots of raw material here. Of course, my parents don't think my job is useless. So not you. So I can safely conclude that if I'm on time, my parents will be happy. So my target sentence for my derivation is if Y, then H. If I'm on time at my job, then my parents will be happy. Now this is a valid argument. The question is, can we demonstrate it using a derivation? So these are our four premises. Right here. If W, then P. If not you, then if P, then H. Not Y or W, not you. Okay, so what is our target sentence? It's a conditional. It's an if-then statement. How do we create conditional statements? Well, we make an assumption of the antecedent and see if we can derive the consequent somewhere down the line. So why don't we start by assuming Y? So we're going to assume Y, and that's an assumption, a sub-assumption off the main scope line, and we're going to try to run a conditional introduction. So now our new target is to try and find H. Where is H? H is buried all the way down here. All right, that's going to be a little tricky, isn't it? How are we going to get it? Well, we could probably get if P then H. How are we going to get that? Well, premise 4 says my parents don't think my job is useless, so we can make some progress right off the bat by saying if P, then H. That's pretty useful. Or one step closer to finding that H sentence. So if P then H, how did we get there? We got there from for to conditional elimination. All right. Now we want that H. How are we going to get it? Well, we need P. All right, where's P? Well, P is at the end of this here. This if W, then P. All right. Well, how am I going to get W? I'm going to get anything. What does anything mean? Why am I alive? Why am I doing this course? I'm tired. Well, let's have a look here. We need W. W is in a conditional, and it's also in number 3 there. Either not Y or W. But hey, we have Y, so maybe we can use kind of a disjunction thing, disjunction elimination. So we have Y, well, either not Y or W, but we have Y. So it can't be not Y, so it has to be W. That's useful. So why don't we just go, you know, some people will ask that you actually kind of do like a double negation. They'll actually say like, you should go not the case that not Y be a double negation. So Y, not Y, and that's, you have your disjunctive syllogism. Some professors will insist on that. I don't. Your mileage may vary, but the point is we have our W here because 5, 3, then we have disjunction elimination. Some people call it disjunctive syllogism as a rule of inference. I'm just going to call it disjunction elimination. So we have either not Y or W. We have the W. If we have the W, of course, then we have the P. Why do we have that? From premise 1 and 7. That's pretty good news, right? And that's another conditional elimination. And if we have the P, we of course have the H. That's also great. Because if P then H, so we have, that's 8, 6, another conditional elimination. Then finally, line 10, we can discharge the whole shebang, and we go if Y, then H. Why do we have if Y then H? Because lines 5 through 9 are one big conditional elimination. Right, so that's how you'd prove that one. Let's do, how about a couple more? This video is getting kind of long, but you should get the idea of how to use derivation systems to prove cool stuff down by now. If you download for all x, right, I printed it out here, you can see that there's lots and lots in section 8.2 and 8.3 of exercises, right? Which hand is that? Whoop, there's that hand. right? So you can consider doing some of them. And if you get stuck with problems, send a comment on this YouTube page. Like and subscribe, Insta, Twitter, Gram, Snapchat. I'm 40 years old. I don't know what you kids are doing. Find me on Kick. I don't know. Okay, I'll pause the video and I'll reset the board. We'll do one more. So here's another problem. It's a tautology. It's a useful tautology because one of the rules I haven't really done a video kind of example for is biconditional introduction. How does biconditional introduction work again? Well, I have to show that they kind of follow from each other. I assume the first, derive the second, then I assume the second and derive the first. And if I can do both of these things, then I can discharge on the main line the whole biconditional. Now this is a tautology, so what I need to do is do this without using any premises, of course. In the video on truth tables, I talked a lot about the different properties of sets of sentences, but in Chapter 8, I ended up focusing mostly on validity and tautologies. But of course, all the other properties of sentences can be proved using derivations as well. In fact, it's pretty easy. If I want to show that something's a contradiction, I can show that its negation is a tautology, for example. In other words, I can derive its negation of the contradiction from the empty set. If I want to show that two sentences are logically equivalent, I just need to derive one from the other. So really, a lot of the cases here are not as interesting as the validity ones or tautology. So why don't we just kind of do this example? So what we have is the very interesting tautology, if B, then not B, if and only if not B. What this is basically saying, these aren't exact, right? This is a very interesting biconditional because it's a tautology. What it's saying roughly is that this statement is going to be the case if and only if not B is the case. That's kind of interesting. So, in other words, not B will be false given the. Okay, let's just work on it. You'll understand as we go on. So what we need to do if we're going to use biconditional introduction is assume one, derive the other, and then vice versa. So let's start with that. So let's start by assuming if B, then not the case that B. This is our assumption, and of course what we're trying to do is biconditional introduction. Now our target here is not the case that B. How are we going to create not B from this conditional? Well, let's assume the opposite. It's either going to be to B or not B. So suppose B were true, and now I'm introducing another sub-assumption, and this one is good before negation introduction. Now if B is true, not B must be true. If not B is true, I've already committed to B. That's bad. So what I have here is from 2, 3 conditional elimination, and then I have 3 reiteration. I'm just repeating myself. So if I assume B, I have a contradiction. So not B must be the case. That makes sense because the only case where if B then not B is the case is when this is false, right? B is false, not B is true. False, true. False, true, true. So good. So if B then not B implies logically not B. How did I get there? I got there. This one is from 3 to 5 negation introduction. So now I've done half of my biconditional introduction. I've shown that from if B then not B, I get not B. Now let's go back to line 7 and let's start a new subderivation where I have to show the other way around. I have to show that not B can generate me if B then not B. How am I going to do that? Pretty easily. I'm just going to, I need to build a conditional. What's easier than building a conditional? Nothing. I just assume the antecedent. So this is, of course, a sub-assumption. It's the same sub-assumption as in 1. I'm trying to build a biconditional introduction. Here I have another sub-assumption. This time I'm going to be doing conditional introduction. And I'm going to go not B. Where did I get that from? 7. I'm just repeating myself. I already have not B as an assumption. So from the assumption of that, I get if B, then not the case that B. And that's from, did I miss some line numbers here? I think I did. So this is 9, that's 10. And on line 11, all the way down here, I'm going to be able to affirm my biconditional because I've shown that from this I can get that, from that I can get this. That's just sheer biconditional introduction. Easy peasy lemon squeezy. Then I can get if B, then not B. if and only if not the case that be. So that was a nice case of a derivation showing us a kind of weird-looking tautology. That's an example actually from the textbook for all x, page 246 on my version here. So again, I can only do so much with these videos and all these examples. What you really need to do is sit down at home and work through as many of these as you can. All right, thanks for watching. It's been a pleasure doing section 1. With the end of chapter 8, the next video will be quantificational logic. We're going to be taking the basic framework of SL and making it more complicated. All right, goodbye.